In this video, we're going to discuss hybrid orbitals and how we can rationalize what happens when we have an s orbital here plus a p orbital, giving something we call an sp hybrid. And in order to do this, we kind of need to discuss how we look at the wave functions of these particular orbitals. So if we have an s orbital, we can graph its probability function or its wave function to look like this. We're going to add to that a p orbital, which is going to look something like this. When we add those together, we're going to get a function that results that if we cut this right down here in the middle right here, we're going to have constructive interference over here on the left-hand side and destructive interference over here on the right-hand side. So what's going to result is a wave that looks something like this. And we can now represent that as an orbital with a node that's going to be right here that has this little lobe right here. So the question you might want to ask yourself is, why would an orbital want to do this, and how can we put this into context? Notice that if we had non-hybridized orbitals, these are going to not interact as strongly as this big lobe right here, which we've drawn for this sp hybrid. So let's try to put this into perspective and talk about the molecule BeF2. We drew BeF2 in a previous section, and here's what we kind of have resulting. Okay, we said this molecule was linear and it had an sp hybridization on the central atom. So the question is, what's the motivation for all of this? So in an atom, we are concerned with reaching the ground state or the lowest energy for one atom. So in an atom, we're trying to achieve the ground state, which would be to get all the electrons in that atom in the lowest energy configuration possible. There are various ways to do that follow our normal electron configuration counting rules, and there's other anomalous electron configurations. But in a molecule, we need to reach the lowest energy for the entire molecule. In many instances, the lowest energy is achieved by promoting one of the atoms to an excited state. And we can say that in general, the strength of a bond is going to be proportional to the amount of overlap. And we can characterize now our bonds into two main categories. There are sigma bonds, in which we have a head-on overlap, where the orbitals that are overlapping are head-on, and there's a pi bond, which is side-on overlap. And what happens is, if we look at our central atom, which is beryllium, we can have a non-hybridized atomic orbitals, where here is our nucleus. We have an s orbital that looks something like this and a p orbital that looks something like this. If they're non-hybridized, the fluorines that are out here, when we pull them closer, are going to experience an overlap based on what that s and the p orbital is. But if we hybridize the s and the p orbital, and when we hybridize these orbitals, the number of orbitals that we hybridize together has to equal the sum of the atomic orbitals that come together. So if we have an s plus a p, we're going to get two sp hybrids. Okay? One of them, if we put the nucleus here, one of them is going to look something like this. The other is going to look something like this. So we have two of these, and if we center them right on the nucleus, they're going to look something like this. And what happens is, when we bring in a fluorine on either side and come to overlap them, the regular non-hybridized orbitals would kind of take up about this much space. So this can increase the overlap with the ligands, which are in this case fluorine. So by hybridizing together, we can look at how these interactions are going to increase, and this will be the driving force to hybridize, because we want to increase the overlap with the ligands so we can form a stronger bond and lower the overall energy of each of these molecules.